Look closely at the night sky. For centuries, we believed that cosmic history followed a tidy, predictable staircase. After the Big Bang, 13.8 billion years ago, there was darkness, a patient cooling, and only then, over hundreds of millions of agonizing years, the very first delicate flickers of starlight. We built our finest mathematical models around this steady, gradual rhythm. Then we sent an instrument out into the frozen quiet of deep space, 1,000,000 miles from Earth. The James Webb Space Telescope unfolded its golden mirror and peered deeper into the cosmic dawn than anyone had ever dared to look. What I saw in those deep field transmissions did not just surprise me, it unsettled me. Tucked into an era when the universe was barely a few 100 million years old, a time when there should have been nothing more than scattered baby stars and fragile gas clouds, we found monsters, fully formed, massive galaxies glowing with the mass of hundreds of billions of suns, alongside supermassive black holes that simply had no right to be there yet. According to our best physics, there was not nearly enough time in the young cosmos for gravity to pull that much matter together. It is the cosmic equivalent of walking into a maternity ward and finding fully grown adults resting in the cribs. Something is deeply wrong with our cosmological story. 3. Either our understanding of how structure forms is missing a crucial piece, or the early universe operated by rules we have yet to uncover. Before we journey down this rabbit hole together, make sure to subscribe so you do not miss any of our explorations into the fabric of space and time. Now, let us examine the foundations of the universe we thought we knew and see where the crack first began to appear. To truly appreciate the puzzle before us, we have to look back at the grand architectural blueprint of the cosmos that physicists and astronomers spent nearly a century piecing together. Imagine looking out across an ancient, undisturbed forest. When you see a massive oak tree with a trunk 10 feet wide reaching 50 feet into the sky, you do not need to check your watch to know its history. You know instinctively that an oak tree cannot sprout from an acorn overnight. A seed must take root. It must absorb water, draw minerals from the soil, stretch tiny green shoots toward the sun, and endure decades of slow, patient seasons before it can claim that kind of grandeur. If you planted an acorn on a Monday and found a 200-year-old oak towering over your lawn on Wednesday morning, you would not simply praise the soil. You would question the fundamental laws of nature for decades. That is precisely how we believe the universe built its galaxies. We called it hierarchical structure formation, or what you might think of as the bottom-up assembly line of the cosmos. Let us trace the timeline. In the beginning, some 13.8 billion years ago, the universe was an intensely hot, almost perfectly smooth soup of fundamental particles. As space expanded, this primordial soup cooled. By about 380,000 years after the Big Bang, 3 electrons finally settled down with protons and helium nuclei to forge the very first neutral atoms. At that moment, the universe plunged into what we call the cosmic dark ages. There were no stars. 3. There were no galaxies. There was only a vast silent expanse of hydrogen and helium gas stretching across total darkness. Now, gravity is a tireless force, but it is also exceptionally patient. 3. The early universe was not completely uniform. There were imperceptible ripples, subtle density fluctuations left over from the earliest moments of cosmic inflation. 3. In regions where the gas was just a fraction of a percent denser than the surrounding space, gravity began its gentle tug-of-war. It was a delicate and painstaking process. 3. A pocket of gas cannot simply collapse into a star on a whim. As gravity compresses gas, the gas heats up. If that heat cannot escape, the rising outward thermal pressure pushes back against gravity. 3. Halting the collapse. To make a star, the gas must slowly radiate its heat away into deep space, cool down, and condense until nuclear fusion finally ignites in its core. 3. This means the first generation of stars took hundreds of millions of years to kindle their fires, and even once they did, they were isolated pioneers. To build a true galaxy, 3,000s and eventually millions of these early stars and small gas clouds had to drift together, collide, and merge. Then those smaller proto-galaxies had to collide again over and over. 3. Slowly weaving themselves into massive, elegant celestial cities over billions of years. Our own Milky Way, a breathtaking spiral containing hundreds of billions of stars, it took more than 10 billion years of cosmic mergers and steady stellar accretion to reach its current size and majesty. Every computer simulation we ran, every equation derived from Albert Einstein's general theory of relativity, and every piece of observational data from our previous space telescopes affirmed this gentle, gradual pace of cosmic evolution. We were confident. We believed we had the rules of cosmic construction figured out. We built our theoretical models on the bedrock assumption that when we look back to the first few 100 million years of cosmic time, we would see only the earliest, most fragile scaffolding of the universe. Faint baby stars, tiny irregular clumps of gas, the cosmos still in its celestial infancy. We were prepared to witness the first hesitant steps of galaxy birth. But when the James Webb Space Telescope opened its golden eye and gathered the ancient, stretched out infrared light from that distant era, it did not reveal scaffolding. It revealed completed skyscrapers. Let us examine what Webb actually saw and why it threatens to rewrite the textbooks. To understand exactly why the scientific community is so unsettled, we need to talk about how we actually look into the past. As a physicist, I am constantly reminded that telescopes are not just giant magnifying glasses. They are time machines. Light has a strict speed limit, traveling roughly 300,000 kilometers per second. When you look at the moon, you are seeing it as it was about 1 second ago. When you look at the sun, you are seeing it as it was 8 minutes ago. But when we try to look back to the dawn of time, we run into a profound obstacle. The fabric of space itself is expanding. 3. As light from the first galaxies travels across the universe for over 13 billion years, the very space it travels through stretches. 3. Think of drawing a wave on a rubber band and then pulling the ends. The wave gets longer and longer. By the time the visible light from the early universe reaches Earth, it has been stretched so far that it falls right out of the visible spectrum. It becomes infrared light. That is exactly why we built the James Webb Space Telescope. We gave it massive, big gold-coated mirrors and cooled it down to near absolute zero so it could act like a pair of cosmic night vision goggles, designed specifically to catch this ancient invisible light. 3. When we pointed Webb at seemingly empty patches of the night sky, we were hoping to catch the faint, delicate glow of the very first star cluster struggling to ignite. Instead, 3. The telescope returned images peppered with what astronomers have started calling little red dots. At first glance, they might not look like much, but you have to remember what you are looking at. 3. We are seeing these objects as they existed when the universe was only a few 100 million years old, a mere blink of an eye in cosmic time. 3. And here is where the mystery deepens into an outright crisis. By analyzing the spectrum of the light coming from these little red dots, we can calculate how much mass they contain. Hey, the numbers simply do not make sense. We found early galaxies containing the mass of tens of billions of suns. They are entirely too massive, too mature, and too brightly lit for an era when the universe was just waking up, but it gets stranger. Deep inside many of these early galaxies, hey, we are detecting the unmistakable signatures of supermassive black holes, and they are terrifyingly huge. In our modern local universe, there is a strict rule. Hey, a supermassive black hole at the center of a galaxy is typically a tiny fraction of 1% of the galaxy's total stellar mass. They grow together in a balanced, synchronized dance over billions of years, but when we look at these early little red dots, that rule is shattered. We are finding supermassive black holes that make up 10, 20, or even an astonishing 100% of the mass of their surrounding stars. Let me put that in perspective for you. Hey, it is as if you discovered a newborn baby who somehow possessed the skeletal mass of a full-grown elephant. It should be physically impossible. Black holes grow by pulling in surrounding gas and dust, but there is a strict natural speed limit to this process. If a black hole feeds too quickly, the friction and heat of the swirling gas generate intense radiation. That radiation blasts outward, blowing the remaining food supply away and starving the black hole. You simply cannot stuff that much matter into a black hole that quickly without it choking on its own meal. Yet, there they are. Hey, lurking in the cosmic dawn, monsters that are millions to billions of times the mass of our sun, sitting in galaxies that are glowing with unimaginable intensity. We are faced with a stark reality. Free. Either the universe had a secret mechanism for building giant black holes instantly, or our fundamental understanding of how the cosmos has evolved is deeply flawed. Free, let me show you the paradox this creates and why it is forcing us to rethink the very nature of gravity and the dark universe. Free. Let us look squarely at the mathematical paradox at the heart of this discovery. In physics, when we run into a contradiction, we do not throw our hands up in defeat. Free. We trace the math step by step until we find the exact place where the numbers refuse to reconcile with reality. Think of a bustling kitchen with a very narrow doorway. Free. Imagine you have a dining hall with thousands of hungry guests, but the food can only be brought out on trays through a single narrow swinging door. If the waiters try to run too fast, they collide. Free. Trays fall, soup spills, and the entire flow of traffic comes to a complete standstill. No matter how much food is sitting in the kitchen, there is a hard, free physical limit to how many meals can pass through that doorway every minute. In astrophysics, that narrow doorway has a name. We call it the Eddington limit. When a black hole feeds on surrounding gas free, the matter does not just fall straight in. It swirls into a rapidly spinning whirlpool called an accretion disk. Free. The gravitational forces and friction inside this disk are so extreme that the falling gas is heated to millions of degrees, turning it into a blinding energetic plasma. 3. That superheated gas shines with furious brilliance, blasting out intense streams of light and radiation. Now, light is not just an ethereal concept. Light carries momentum. If photons exert actual physical pressure, so you have a violent cosmic tug-of-war. On one side, the colossal gravity of the black hole is pulling matter inward. On the other side, the ferocious radiation generated by that very same falling matter is pushing outward. If the black hole tries to swallow matter too quickly, the outward blast of light becomes stronger than the inward pull of gravity. It literally blows its own food away into deep space, starving the black hole. 3. This creates an unbreakable speed limit on how fast a black hole can grow. Under normal physics, the maximum rate at which a black hole can double its mass is roughly every 40 to 50 million years. 3. Now let us do the cosmic bookkeeping. In our standard picture, the first black holes were born when the very first massive stars died and collapsed. 3. These seeds might have started with the mass of maybe 100 suns. To grow from that humble seed into a monster of 1 billion solar masses, that black hole has to double its mass over and over again, more than 20 times in unbroken succession. If every doubling takes 50 million years, you need at least 1 billion years of continuous uninterrupted feeding at the absolute maximum possible rate without pausing for a single second. Yet 3, the James Webb Space Telescope is finding supermassive black holes that already weigh hundreds of millions or billions of solar masses when the universe was only 400 or 500 million years old. 3. Do you see the contradiction? The cosmic clock had only ticked for 400 million years, but the black hole required at least 1 billion years just to eat its lunch. 3. It is mathematically impossible within our standard model. It is like meeting an 80-year-old master craftsman in a village that was only founded 20 years ago. 3. And the paradox does not stop with black holes. We face the exact same problem with the stars inside these early galaxies. When stars form inside a gas cloud, the biggest and brightest stars ignite with terrifying fury. They blow off powerful stellar winds and eventually detonate as supernovae. 3. These cataclysmic explosions blow the remaining gas out of the galaxy, temporarily turning off the star-making machinery. Because of this self-regulating cycle, galaxies in our universe are typically quite inefficient at making stars, turning only a small fraction of their available gas into stars over billions of years. But to produce the massive and brilliant galaxies that Webb is uncovering, these early cosmic nurseries would have had to convert almost 100% of their available gas into stars almost instantly, with zero pause, zero waste, and zero disruption from supernova explosions. Every standard rule of astrophysical feedback Every law of stellar evolution and every cosmic time constraint we have spent generations refining is being pushed right to the breaking point. This is the paradox. 3. The universe is telling us that our timeline is missing something radical. In the next chapter, we are going to explore the mind-bending theories physicists are putting forward to solve this riddle, and some of them will break your brain. When standard physics hits a wall, we have to be willing to entertain ideas that sound like pure science fiction. 3. If the universe refuses to follow the schedule we gave it, then we have to consider that nature found extraordinary loopholes to bend its own rules. 3. Let us explore the radical ideas physicists are debating to solve this crisis. Prepare yourself, because these concepts take us right to the jagged edge of modern physics. 3. The first possibility is what we call direct collapse black holes. In our everyday world, if you drop a ball of dough, it flattens out, but it stays relatively together. But in space, 3, when a giant cloud of gas collapses under gravity, it normally breaks apart into thousands of smaller fragments, giving birth to a cluster of ordinary stars. 3, this fragmentation happens because cooling molecules allow different parts of the cloud to collapse independently. 3, what if the earliest cosmic nurseries were so intensely bathed in ultraviolet radiation from nearby stars that the gas was prevented from ever cooling down into molecules? Without molecules to cool it, 3, the cloud cannot fragment into small pieces. Instead, an unfathomably colossal cloud of pristine gas, containing the mass of a million suns, collapses all at once as a single titanic structure. It completely skips the star phase. It does not ignite fusion. It simply caves in under its own crushing weight, collapsing directly into a gargantuan black hole seed with the mass of 100,000 suns in one singular stroke. By skipping the slow step-by-step process of stellar birth, the universe gets a running start producing a seed so enormous that it can easily grow into the monsters Webb is detecting today. But what if the seeds were planted even earlier? This brings us to an idea that I find deeply compelling: primordial black holes. What if these cosmic titans did not form from matter collapsing in space at all? 3. What if they were baked directly into the fabric of the universe in the first microsecond of creation? During cosmic inflation, in the tiny fraction of a second, immediately following the Big Bang, quantum fluctuations rippled across space. In some regions, the energy density may have been so extraordinarily high that the fabric of space itself simply collapsed into black holes instantly. Long before the first atom, let alone the first star, was ever assembled, these primordial black holes could have been drifting through the darkness from the very beginning, acting as invisible, prepackaged gravitational anchors. When the cosmic dark ages finally ended, these ancient black holes were already sitting there ready to pull gas toward them like cosmic vacuum cleaners, jump-starting the growth of galaxies billions of years ahead of our predicted schedule. And then we arrive at what might be the most exotic possibility of all: dark stars. When we think of a star, we think of an engine powered by nuclear fusion, smashing hydrogen atoms into helium like our sun does every second. But in the early universe, when dark matter was packed much more densely than it is today, conditions were vastly different. Theoretical physicists have calculated that as the first clouds of hydrogen and helium began to condense, they could have captured immense amounts of dark matter at their cores. If dark matter particles are their own antiparticles, they would collide and annihilate one another, releasing pure blinding energy. This creates a truly bizarre cosmic entity, a star powered not by nuclear fire, but by the annihilation of dark matter. Because dark matter annihilation generates heat without igniting a runaway nuclear fusion reaction, these dark stars would never get hot enough to blow themselves apart. They could continue to swallow gas and grow into puffy, gargantuan leviathans billions of kilometers wide, shining with the brilliance of millions of suns, yet surprisingly cool on their surfaces. When their dark matter fuel finally ran out, these colossal dark stars would have collapsed entirely, leaving behind the massive black hole seeds that now haunt our telescope images. These ideas are startling, but they are not idle speculation. They are the logical consequences of taking our fundamental equations and mushing them into untamed territory. Yet, as fascinating as these exotic theories are, maybe the truth might be even more disruptive to our worldview. In our next chapter, we must face the hard, uncomfortable reality of what these observations might be saying about our standard model of cosmology itself. 3. Now we have to confront the uncomfortable reality that every theoretical physicist must eventually face when new data shatters our comfortable assumptions. In science, there is a natural human temptation to want a dramatic revolution. We love the narrative of an ancient theory being instantly torn down by a single heroic discovery, paving the way for completely new physics. But real science is far more demanding and far more rigorous. When you discover something that seems impossible in an old house, you do not immediately conclude that the laws of gravity have failed. First, you check if the foundation shifted. You check if the floorboards warped. 3. You check your own measuring tape before you declare that space itself is broken. Right now, the cosmological community is locked in a fierce, essential debate over whether the James Webb findings represent a failure of our astrophysics or a fundamental crisis in our standard cosmological model. Let us examine the first, more conservative, hard truth. Our instruments might be revealing a trick of cosmic light. When we calculate the mass of a galaxy billions of light years away, we cannot place it on a physical scale. 3. We measure the photons of light reaching our mirrors, and we infer the mass based on our understanding of how stars shine. 3. But remember those supermassive black holes feeding furiously at the centers of these early systems. When a black hole consumes matter, its swirling accretion disk shines with a brilliance that can easily outshine all the stars in the host galaxy combined. If our current computer models fail to completely separate the blinding glare of the feeding black hole from the gentle glow of the surrounding stars, we might be dramatically overestimating how many stars are actually there. What looks like a galaxy containing hundreds of billions of stars might actually be a much lighter, younger galaxy hosting a roaring, hyperactive black hole that is throwing our calculations off balance. Furthermore, we make assumptions about the types of stars being born. In the local universe today, stars are born in a standard distribution. For every giant, brilliant blue star, there are hundreds of smaller, dimmer, red dwarfs. But in the pristine, unpolluted environment of the early cosmos, with no heavy elements to help gas cool, perhaps the universe favored producing only titanic, ultra-bright monster stars. If the initial stellar population was top-heavy, a galaxy would shine with blinding fury while containing far less total mass than we originally estimated. If this is the answer, it means our basic timeline of the universe remains intact, but our understanding of early star birth, dust physics, and black hole accretion was vastly oversimplified. It means we have a tremendous amount of astrophysical homework to do. Yet, there is a second, far more unsettling possibility that we cannot ignore. What if our mass estimates are correct? What if the universe really did manage to build massive, very mature galaxies and billion solar mass black holes within a few 100 million years of the starting gun? If that proves to be true, the crack goes straight down to the bedrock of our understanding. 3. It means our standard model of cosmology, known as the cold dark matter model, is fundamentally incomplete. This model has been the crowning jewel of modern astrophysics for decades. 3. It has successfully explained the cosmic microwave background, the large-scale web of galaxies, and the abundance of primordial light elements with breathtaking precision. 3. If this standard framework cannot accommodate the rapid assemblies of these early structures, we may be forced to reconsider the fundamental ingredients of reality itself. We might need to rethink what dark matter actually is. Perhaps dark matter is not just cold and collisionless, but possesses exotic self-interactions that allowed it to clump together far more rapidly in the early universe, creating gravitational wells that dragged ordinary matter together at breakneck speed. Or perhaps the dark energy driving the expansion of space is not a simple static constant, but a dynamic, evolving field that altered the pace of cosmic history. This is the hard truth. 3. We are caught between two profound revelations. Either we must radically revise the violent, chaotic mechanisms of how stars and black holes are born, or we must rewrite our story of how the cosmos itself expanded and evolved from the very first moment of creation. In our final chapter, we will bring all these threads together to understand what this means for our place in this vast, evolving reality. When we first stared at the data returned by the James Webb Space Telescope, the sheer scale of the early galaxies felt like a fatal blow to our understanding of the universe. We were backed into a corner. We had to either accept that space and time behaved in completely unrecognizable ways during the cosmic dawn, or admit that we were fundamentally misinterpreting the light we were seeing. Science, however, is a relentless process of refining our vision, and just when the cosmological crisis reached a boiling point, the universe handed us a profound revelation. 3. The breakthrough came when researchers focused their attention on a specific, extremely distant object, one of those mysterious little red dots, dating back to when the universe was only about 660 million years old. We expected to find the spectral signature of a massive, sprawling galaxy teeming with billions of mature stars, but the light we analyzed did not match a galaxy at all. It told a story that was far more concentrated and far more bizarre. We discovered what I like to call a black hole star. I want you to picture something entirely new to our astrophysical catalog. Imagine an extraordinarily dense, turbulent cloud of pristine hydrogen gas packed into a space roughly the size of our own solar system. Now place an active, out-ravenous black hole containing the mass of perhaps 100,000 suns right in the center of that dense cocoon. 3. Because the gas is so incredibly thick, the black hole is practically choking on its food. As the matter spirals inward, it generates ferocious amounts of radiation. 3. But that radiation does not just stream out into empty space. It crashes into the dense surrounding envelope of hydrogen. The gas absorbs that immense energy, scatters it, and re-emits it, thereby causing the entire solar system-sized cloud to glow with a blinding, brilliant red light. And when I say blinding, I mean this single compact object is pumping out energy 100 billion times greater than a normal star. This changes the entire board. When we first looked at those little red dots, we saw an astronomical amount of light, because we assumed that light was being produced by the slow, steady nuclear fusion of ordinary stars. We calculated that these objects had to contain the mass of tens of billions of suns. We thought we were looking at impossibly massive, fully grown galaxies. 3, but we were being deceived by a cosmic mirage. The mass was never there. The universe did not break the laws of physics to assemble gigantic galaxies overnight. Instead, nature found a way to create a hyper-efficient, ultra-bright light bulb in the early cosmos. The blinding glare of these black hole stars simply outshined everything else, thereby tricking our initial models into overestimating their size by orders of magnitude. For the theoretical physics community, this discovery is a profound relief. Our standard model of cosmology, with the beautiful framework that describes the steady expansion of space and the gradual assembly of structure, remains intact. The foundation of our universe is not broken, but our understanding of the objects that inhabit it just became wildly more fascinating. We now know that the cosmic dawn was populated by these bizarre gas-enshrouded monsters lighting up the dark ages like isolated lighthouses in a vast, empty ocean. Every time we look deeper into the universe, we are humbled. We are reminded that our models, no matter how elegant, are just approximations of a reality that is vastly more complex and creative than we can fully anticipate. The story of these impossible galaxies is a perfect example of how science actually works. It is not a rigid set of dogmas. It is a living, breathing dialogue with the cosmos. We make an observation, we find a contradiction, we panic for a moment, and then we dig deeper until the universe reveals a new layer of its truth. If this journey into the deepest, most perplexing mysteries of the cosmos expanded your perspective today, please consider supporting our work by using the Super Thanks button below. Your support directly funds our ability to keep untangling these cosmic puzzles and bringing the absolute cutting edge of physics straight to you.